Okay guys, so looking at maximum and minimum problems, in class we've talked about the fact that we can only differentiate these functions if they're in one variable. So today we're going to look at some problems where we're not given the function and we have to come up with a function or a rule in one variable so that we can start analysing the maximum and minimum. And the thing that we need to keep in mind when we do this though is that when we find a stationary point, what we're finding is a local maximum or a local minimum. And that may not be the absolute maximum or minimum value for that function. So if our function has an endpoint, then we need to check that as well, because that could be the value that we need in order to answer the question. So these maximum and minimum problems are really useful in real world situations. So things like companies, they want to minimize costs, maximize profits. If we're talking about cars, you want to minimize fuel consumptions while maximizing performance. And while you may be able to go further on performance, it's not necessarily going to give you the best return on the fuel that you need to put into the car. So the problems that we're going to look at are quite simple and obviously not as complicated as most of the real world applications, but they are used quite a lot. So looking at this first example, a farmer wants to fence a rectangular paddock. He's got 120 metres of fencing and we need to find the maximum area that he can build using that amount of fencing. So the thing that we have to remember is generally what we would do is say, oh, okay, we've got this paddock and we're going to make this side X and this side Y. But that's not going to help us because when we do the area, we're going to say X times Y. We've got two variables and we can't do that. So what we're going to do instead is say, well, if I call one side X, what does that mean? Well, that means that this other side is also going to be X. And what do I use for the other side? Well, it's going to be 60 minus X. I want you to think about that and tell me why it's going to be 60 minus X. So for this one, we're going to say let the width be X. So then the length is 60 minus X. Okay? So what we're looking at is maximizing area. So I need the area function, and for this one, that's going to be X outside of 60 minus X, isn't it? All right, so if we're going to be differentiating, this is going to be much easier to differentiate if I expand. So area is 60x minus x squared. So then if I want to maximize that area, I need to differentiate the area function in order to be able to find the stationary points. So the derivative of a with respect to x is equal to 60 minus 2x. That's pretty simple. It's not a complicated function. All right, and that will be maximized when the derivative is equal to 0. Okay, so don't just write down 60 minus 2x equals 0, because 60 minus 2x is going to be equal to a lot of different things. You need to actually state what it is you're doing. We are trying to maximize a, or you can say the stationary point, either, but let them know what it is you're working on. All right, so 0 is equal to 60 minus 2x. Now, this is a very easy function to work out. X is equal to 30. So we get the maximum area if one side of our rectangle is equal to 30. So think about that. We've got a rectangle. One side is 30, which means this side is 30. If the whole thing is equal to 120, well, 60 minus 30 is going to give you 30. It's maximized when we've got a square. Now that's something that conceptually we can understand quite easily. The maximum area is given by a square rather than any other type of rectangle, right? Now, once you've worked that out, you need to go back and make sure that you are answering the question that has been asked. Okay, so the question says find the maximum area. So if you were to do this and say, oh yeah, it's maximum when x is equal to 30, you haven't answered the question, you automatically lose a mark. And that's a rather simple thing to lose marks on. You can find the area of this paddock, right? So therefore, a is equal to 30 outside of 60 minus 30 which is 900. And in this case, we're talking about square meters, right? So we have the maximum area is equal to 900 square meters. All right, more complicated. A sheet of cardboard measures 15 centimeters by 7 centimeters. 4 equal squares are cut from the corners and the sides are turned up to make an open rectangular box. Find the length of the squares to be cut out to maximize the volume of the box. Whenever you get something like this, I would strongly suggest that you draw yourself a little sketch so that you know what's going on. Okay, so the first thing we have is this rectangular piece of cardboard, and we know that it's 15 centimeters by 7. And then they're going to cut equal squares out of the corners. So we're cutting out the squares. Now, we don't know what lengths they are that we're cutting out, but once they cut those out, we are going to have an open rectangular box. So you can see how when they cut those out, you can fold it up. There's no lid. We're making a box that's open at the top. And what we want to do is maximize the volume. So not area this time, we're talking about volume. So if we started off with a length of 15 centimeters and a width of 7, and we're cutting out some unknown length to make these squares, that's going to be our x. Okay, so name your unknown and then go back and say, well, what does that mean to my diagram? All those little bits that we're cutting out are x. So if we originally started off with 15 centimeters, then after I cut out these squares, the length that I'm left with, so when I fold it up, the length of my rectangular box is going to be 15 minus 2x, because we've cut these two lengths x out. Similarly, what's going to happen to the 7? Well, we started off with 7, but we're going to cut out 2 x's, so that width there is going to be 7 minus 2x. And then what's the height of our box going to be? Well, if I fold it up and I've cut out x, the height is obviously going to be x. Okay, so working out the volume function isn't terribly difficult. It's a rectangular box. It's going to be x times 7 minus 2x times 15 minus 2x. All right. So expand that out. I would expand out one of the sets of brackets and then the second one. Once you're done, it's 4x cubed minus 44x squared plus 105x. Okay. Now before you get into the differentiation and all the other steps, because we launch into that, that's what we've been studying, that's what we've got to do, and we go straight into it. I want you to stop and think, what kind of conditions do we have on x? Okay, so this is where you go back to your diagram and you have a look and you say, well, how long can x be? What width can we cut out for these squares? Because we are talking about a practical problem here, and I could make this negative quite easily, but I can't get a negative length for a box. So once we come back to real world problems, we have conditions that we haven't encountered before, and you need to consider those in maximum and minimum problems. All right, so what are the parameters for x? What domain does this function exist in? Well, x has to be greater than 0, right? It can't be equal to 0, because if I don't cut anything out, I can't fold it up and I can't make a box. So it has to be greater than 0. What's the maximum that x can be? Maximum length, well, can't go past 3.5, because if I cut out 3.5 from either side, 7 minus 2 times 3.5, 0. I've got no box again. So x has to lie somewhere between 0 and 3.5. And that's going to become very important, which you'll see once we start differentiating. Okay, so come up with your function, think about what kind of parameters we're putting on x before we get into the differentiation. So I have my volume function, 4x cubed minus 44x squared plus 105x. Now I'm going to differentiate it because I want to maximize something, which means I need to find stationary points. So The derivative of v with respect to x is equal to 12x squared minus 88x plus 105, right? And the volume is maximised when that derivative is equal to 0. So make it equal to 0. And then you've got a choice. You can start trying to factorise, or if it's too complicated, just go to your quadratic formula. This one does factorise, and that's fine. But you don't want to spend too long trying to factorise these guys. Like if it's not working, go to your quadratic formula. You end up with 2x minus 3, 6x minus 35. Okay? So what does that mean for x? Well, therefore, x is equal to either 3 over 2, so 1.5, or 35 over 6, which is 5 and 5/6. Does anybody see a problem there? Now, this is why you have to consider, in reality, what x can and cannot be. X can't be more than 3.5. So x cannot be equal to 5 and 5/6, or 35 over 6. Please state that. Let the examiner know that you know what's going on here. Okay. So the question wants you to find the length of the squares to be cut out to maximise the volume. They're not asking us what the maximum volume is here. They're asking us what length it is. Okay, so we found the length, but is it the maximum? That's something that we need to check. Okay, so just double check. You've got a choice. You can either use your second derivative, which is what I'm going to do, or you can use your table and work out what it is on either side. So that second derivative is going to be 24x minus 88, and when x is equal to 3 over 2, the second derivative is equal to, straight into your calculator, you're going to get negative 52. So therefore it is concave down, and our function is maximised when x is equal to 3 over 2, or 1.5 centimetres. Okay? That's what you need to do exercise 2.10.